and I'm going to pull this until I get 22 pounds of force on these baggage scales. And we're going for 22 pounds, 18, 20, 22. Welcome back to Workshopfriend, and this is my 9th video on renovating my small horizontal milling machine. Today I hope we can start working on this casting for the overarm support bracket, which I had cast about several months ago. Today what I want to do is face it and start the boring of the 3 holes. But before we get to that, I want to just pick up on something at the end of the last video, and that was deflection of the overarm support bar, which I fitted in the last video. Some of you might have been surprised at the degree of that deflection, but what I'd like to do today is just to verify by measuring more accurately and also by calculation how much deflection we can really expect. In the comments section of the last video, when I made and fitted this bar, someone made the interesting comment that it would be a good idea maybe to check how parallel this is with the table. That's a good question, but for me a more immediate question is how parallel this is to the axis of the machine. And I've put in here an International 40 1 1/4 inch arbor with its spacers and also the journal here, and I'm going to use that to check this height in this position and then as close as possible to the head as possible here. And so by measuring the diameter as accurately as possible, the diameter of the journal, and checking with slip gauges, I should be able to work out the spacing. So before doing that, it's a good idea to verify what run out there is on the shaft here. There's bound to be some. Yeah, we've got about 1/4 of total run out there. Perhaps that's not surprising. I have tightened the nut up here so everything is compressed. Yeah, maybe that's not surprising, I don't know. It'd be interesting to know what other people have on their machines. So we've got 1/4 run out. I did check how good a fit this journal is on the arbor itself, and it is a good fit, and that doesn't have any run out, any measurable run out. So what I'm going to do is just set this to the average position, so which is there, and then we will try the slip gauges. So we know the diameter of the shaft, we know the diameter of the journal, so if we can precisely determine the distance between these two, we can work out the center distance. Okay, I'm going to fiddle around with this and get the best measurement I can. Okay, again we'll just check for a run out. Not surprisingly, that's much lower. The run out here is around about just under 1 thou. So again, I'll just go for the average reading, and we'll use the slip gauges again to check that height. So I've taken these measurements and put them in on this chart. This represents the front face of the milling machine. This is the support bar which we machined in the previous video, and this is the 1 1/4 inch arbor. This is the journal shown in 2 positions, and here we have the 2 stacks of slip gauges. I also ensured that the run out on the shaft was eliminated by taking an average reading, and also I measured the bar at the 2 positions, and this was in fact 2.500 and this was 2.501. So I've taken that into account in doing the arithmetic. Now the original center distance, which I had expected, was 6 inches, but it turns out that it's actually nearer to 5.9978 and 5.9975. And perhaps realistically we should just say 5.998 and 5.998. So a couple of things that I gained from this. First of all, how remarkably accurately these two holes have been bored out. Less than 3/10 of a thou that I could pick up anyway, over a distance of 11 inches, which I think is remarkably accurate. And the second thing is that in boring these two holes, ideally I want to aim not for 6 inches, but 5.998 inches between the two centres. So assuming our cutter is mounted in somewhere in the middle of this arbour and it's rotating in this direction, then it's going to exert a force on the arbour in this direction away from you. So the job of the support arm obviously is to, when the journal's in this position and there's a bush in here, is to provide some support. And that's going to place two forces on this bar. One is going to want to rotate it in this direction, and it's also going to want to bend it in this direction. So this bar is going to be subjected to basically twisting and bending. Now I realise that calculations analysis is not everybody's cup of tea. If that's the case and you want to go straight to machining the castings, then go to this point in the video. If you want to see the calculations, then stay with me here and I'll take you through what I've worked out and what the results were and how that compares with actual measurements. I started videoing this and I was thinking to myself, this is just getting too involved and probably very few people are going to be interested in this. But I'll just give a quick overview just to show that I worked this out and where it's all come from. So this is just a sketch of the layout. We've got the support bar, the arbor and the bracket on the end here. The cutting force is in the middle, but that's transferred to the end here. And this force here, F, will result in a total deflection X, and that's what I want to work out. I'm assuming for my calculations a force on the end here of 22 pounds, which is 98 newtons or about 10 kilograms. You can look at this from 2 points of view. One is bending and one is torsion. So for the bending calculation, that's the beam fixed at the end here, cantilevered. And for torsion, it's fixed at the end here and we're twisting it. So the two relevant equations are here. We need some data to go along with that. That is Young's modulus for compressive and tensile stresses, which I've got from data sheets. I can work out the second moment of area, plug that in to the equation, and we come out with a deflection here due to bending of 0.011 millimeters for 10 kilograms of force, or 22 pounds, and that is half a thou. I've done the same thing for torsion, and you come out with an angular movement, and that figure's not very helpful, so I did a bit of trigonometry and resolved that angular movement into a movement at the end here, and that comes out at 0.012 millimeters, or half a thou. Now, is that coincidence or is that by design? I tend to think it's probably by design, that whoever did the calculations on this originally thought that maybe equal bending deflection and equal rotational deflection might be a good idea, and hence the proportions relative to the radius of the arm. I don't know. What I like to do now is go over to the machine and actually measure the deflection and see what result we come up with. I did this last time, just approximately, but I'd like to do it a little more accurately this time. This is our setup. Bolted this on the end here so that I can get the DTI in a sensible position, because I've got these baggage scales here, roughly in the position where we did the calculations, in the center of where the bracket will come. And I've set the DTI on 0, and we're going to pull it in this direction and measure deflection. I'll move in a bit closer so you can see the DTI, and I'm going to pull this until I get 22 pounds of force on these baggage scales. 7, 11, 13, 15, 17, 18, 20, 22. So I think that was just over half a thou. So there we are, our bending calculation is correct. I can't do the angular deflection at the moment because we haven't made the support arm, and I'll also later on work out how rigid the arbour is and what difference that makes. But anyway, that just gives an idea of what kind of movements we see in this kind of milling machine. Anyway, the purpose of this was just my own interest really, I guess, to know how flexible this setup is and the relative stiffness of the arbour as compared with the support arrangement. And so far what I've learned is that this is much more flexible than this. And the other thing I've learned is that the angular flexibility is equivalent to the bending flexibility. Later on we'll be able to check the full calculation once we've made the support arm, and then we can actually put a load on the lower end of that, and we can see what angular movement there is as well. What's the purpose of this? Well, I think the purpose of it is just my own curiosity, but it's also to know what's important in a setup like this. How important is it to have all of this perfectly aligned, and how much is the load shared by the support arm, and how much is just due to the rigidity of the arbour itself. And I think the conclusion I've come to is that the support arm is dominant, and this is relatively flexible. Well, it's taken a long time to get to this stage. Now, having machined the overarm support bar, I have an accurate diameter to machine this too. Also, a couple of videos ago, I finished restoring the vertical head, so we can use that now with confidence. It doesn't leak oil, and I know that everything is set up properly and the bearings are adjusted. So the first operation at last on this support arm is to machine these two surfaces, to skim them flat. I have dressed up the casting, removed as much flashing as I can, and I pay particular attention to this bottom surface here so that it fits snugly on the table. So I've clamped it down in 3 places, and I'm going to first of all skim this surface and then this one. It was unavoidable to have the clamp covering an area which needed to be machined. So I carefully removed the clamp, leaving the setup as it was, and relocated it so that I could just finish off that missing area. And with a bit of care, I was able to achieve a good blend between the two cuts. So I've cleaned everything up and got a nice clean table to work on, cleaned the component, and I've mounted it on its machine face here. This is a nice large diameter. So with a clamp through the middle here, I can be sure that it's all square with the table. And at the moment this clamp isn't tightened up, but I've got a little jack here which is made from a 3/8 bolt and nut with the two ends machined square, and I can insert this now and just get that so it's just beginning to take some pressure there. Just adjust that slightly. I'm going to make sure that the bolt is as close as possible to the work, so as much of the clamping force is going into the work as possible and only what's necessary into the packing. I'm going to put this clamp on this side. I might move this along here a bit more so that we can get more even distribution of clamping force. It's just enough space to get in there with a cutter. And then we'll replace this on the rear. So here we have the casting, both sides skimmed flat, and that gives nice location surface for mounting on the milling machine. I haven't done these surfaces yet. They're probably going to be next on the list actually. But in between, I've had a look at how I'm going to actually bore this out, and the first thing that's obvious is that my boring head's not going to reach all the way through, even with an angle cutter in the end here. So I've made up this little tool holder, and that can go in here. And it can give me just that extra bit of length to go right the way through this longest hole. The next question is going to be how I'm going to set this up, whether I'm going to bore it vertically or horizontally. And I think the horizontal option is going to be best. If that is the case, then I'm going to need to machine these surfaces first, so that I can mount the casting on the table and have access for boring like that horizontally. And one other advantage of doing it this way is that I can move the table across if I need to, and I can also measure the hole from this side, from the outside. So I think that's going to be the preferred option. So I'm going to whip the head, the vertical head, off the mill and get this set up for the next operations. It was now necessary to determine the center line of the casting so that I can machine these bosses square. And to do that, I took into account the draft angle on the two large bosses, and knowing their diameters, I was able to align that with the front face of the table. Bit of careful adjustment, and I was able to determine the center line of this casting and bolt it down ready for machining. So these two faces will form a reference for subsequent machining operations, so it was quite important to get this set up correct. This is the setup I use for machining the second face parallel to the first. I have a parallel clamped to the machine face, and again I'm measuring that from the front face of the table. So I've had to just adjust things slightly. I've had to lift the casting so that the center line of the boring head allows me to clear the table here. So old ball races are very helpful, I find, for jobs like this. So I've used one here as a spacer just to lift this up, and of course the advantage is that they're nice and parallel. So what I'm doing now is just clocking on the front face, or the rear face I guess, from where we're standing, and just getting this parallel with the machine axis, and then we can set up for boring.
I'm also going to clamp this end. I don't think that's enough really for such a big job as this. So this end I'm going to clamp, and I've just put a little jack there underneath. And so just to get the boring operation underway, I'm going to align the outer diameter of the boring head with the casting, and they're similar diameters, so they're quite easy to line up. And then as we get closer to the final size, we will make adjustments as we go along, but this will just get us going and we can start roughing out. There's a large lump here which is left over from the core, the cross core, and so I've got to machine that out first. So I'm just setting the boring head to the minimum diameter to get going. We're going to have to cut that out first before we can get a good clean cut all the way through. Now, of course, I'm only using high-speed steel here, so I expect to be doing a lot of regrinding as I go along. If I had my silver soldering equipment here, it's in Pakistan unfortunately, but if I had it here, I'd probably make up a cutter with a tungsten carbide tip. But anyway, I have to make do with what I've got. So far I haven't reground the tool, but it is beginning to show signs of wear, so I'm just going to remove the tool holder and we'll have a closer look at the high-speed steel bit. Well, as expected, the tool has taken quite a hammering, as you can see here. That's not surprising considering we're going through this mixture of sand in the outer, sand and iron in the outer layer of the casting, and it's an interrupted cut. We'll keep going, so I'll give this a regrind, we'll keep going, and hopefully we'll soon get through that horrible outer layer. Okay, we're almost right through the outer skin of the casting. There's just a small bit left there. So I'm going to take a little break now. When I come back, I will touch up the tool again and we'll get right through that. And then boring should be a bit more straightforward. Well, once again, time has beaten me and I've not completed what I'd hoped to do in the one video. But I'm not rushing this because I don't want to make a mistake. This casting I obtained with some difficulty, so it's somewhat precious. Next video I'm going to size these two holes, and this is very critical, this one. Also the spacing is critical and I need to think about how to get that spacing correct. Also boring for the cotter and then making the cotter. Once again, if you've appreciated the video, then do give me a thumbs up and consider subscribing if you've not done so already.